Okay, so probability fundamentals. So we're going to look at the fundamentals including your sample spaces stuff, how you handle multi-stage experiments, union, intersection, your probability tables. All this stuff is stuff that we've done before, not necessarily in these classes, but stuff that you would have certainly done in previous years of math. So a lot of this will just sort of be review. Starting with our sample spaces. So let me get the screen share up for that. Cool, okay, there we go, that'll be better. Yep, so sample spaces, what are we talking about here? We are talking about simply the possible outcomes of a given scenario. So in the example that I'm giving here in our notes, it's the sample space of a six-sided die. So you got the numbers 1 through 6. Now, the generic probability equation to solve any probability is going to be the number of desirable outcomes, x, divided by the total number of possible outcomes, n. Right? So, for instance, if you have a bag of 10 marbles, 3 are blue, 7 are red, the probability of finding a blue marble is going to be based on how many blue marbles there are, divided by how many total marbles there are. There's a whole bunch of different other examples I've got here, different sample spaces as prescribed to the different experiments that we have. As for when you get your probabilities of areas, it's a very similar idea, but instead of having like discrete outcomes, you start thinking about things in terms of desirable area versus total area. So with that in mind, if you wanted to, for instance, find the probability of a dart hitting the red in this dartboard, well, what you want to first do is figure out the area of the area you're trying to hit, which in this case is going to be the area of the circle, and then from there the total area, right, which is going to be the entire dartboard itself. We're not going to exclude the red bit from there because we're trying to find the total area of the board itself as a reference of like our total sample space, or so it can be thought of. That gets us our two outcomes, divide them up, and you get the probability of finding what you're looking for. I know we had a few late arrivals here, so I'll just quickly clarify. I'll quickly ask, is there anything that needs further clarification on that? So far, I'm going to be looking at probability fundamentals, and then later we'll cover a few student-submitted questions. Any questions about where we're at so far? If not, feel free to let me know. Happy to go back. Next up is this idea of complement probabilities. So this is where we understand that the probability of all outcomes in a given experiment needs to add up to 1. And so, given that being the case, if we know the probabilities of every other outcome excluding one of them, well, we know that everything has to add up to 1 anyway. So we simply figure out the ones that we do know, add them up, and then whatever we don't know has to then finally add up to 1. A very basic example, we know the probability of a head is a half, and let's pretend we don't know the probability of a tail. Well, there's only 2 outcomes in this experiment, head or tail. If head is a probability of a half, and all experiments have to add up to 1, I've got head plus tail, half plus something has to equal 1, which, sure enough, we're going to get half again. That's a very, very basic example. Obviously, you wouldn't need to do it for that, but it's more so helpful for when you have these. I mean, even this one's kind of easy to do, but more so when you have, as we'll get into it later, when we start looking at binomial, you'll start to have undefined sample sizes where the number of outcomes isn't necessarily known. It's just an n in the example. And so that's where using complement probabilities can help you circumvent not knowing how big n is. You can start going backwards. Like for instance, probability of getting a number greater than 1 is well and easy to calculate just by looking at this, right? 5 out of the 6 numbers are greater than 1. But if you don't know this ends at 6, you don't really know what your denominator is. And so what you can do instead is say, well, okay, I know that the probability of rolling a 1 is a 1 out of 6, so whatever the number of outcomes are on the other side, I know the remainder has to be 5 out of 6 for that remainder of outcomes, because it has to all add up to 1. So it'll make more sense when you start looking at the actual examples where they have unbounded sample sizes, but for now we're just thinking about complement probabilities, the fact that all things in a scenario have to add up to 1, and we're just making use of that to potentially simplify some of our results. Any questions about that so far? Because that's pretty much it. That's our sample spaces stuff. Okay. Next up, so with the sample spaces stuff, they were pretty self-contained experiments. They were quite simple things, you know, rolling a dice, tossing a coin, that sort of thing. What we're looking at with multi-stage experiments is what happens when you're repeating those experiments over and over again, or potentially even combining experiments. Like the basic example is going to be tossing a coin multiple times. You know, what's the probability of tossing a head 2 times in a row? One of the main tools we can use for that is tree diagrams. So tree diagrams are a nice visual way of representing all the outcomes in a given scenario. You have, depending on how many outcomes there are per stage, will be how many initial branches you have, and then depending on how many stages you have, will determine how many additional branches you add on to that. Now, a lot of these terms may or may not make a whole lot of sense. You would have mostly seen them before, but it might have been a while. For those who need a quick refresher, these are like conditional probabilities. When you have this pipe symbol here, the straight line symbol, kind of like how you define your domain. And these are intersections, so basically the combining of multiple outcomes. Conditional probabilities simply exist with respect to something else having already happened. So what you'll notice is, for instance, if you take this branch of probability of A, any further probability that branches off of this is conditional based on having gone through branch A. Same thing here, A naught, the opposite of A. Any probabilities from that point on are now conditional on having gone down that branch of not A. Each of the branches that you have on your tree diagram are going to be labeled with the probability of taking that path. That's what all these mean. They're going to end up being numbers when you actually use them, and they are the probability of taking that path. I think I talked about this one. And as for how you end up using it, typically what you're trying to do is figure out any of these at the very back end. You're trying to figure out those probabilities. Probability of this happening and this happening, or this happening and this happening, for instance. That's what all these are representing here. As for how you find them, all you're doing is multiplying along the branches. So in other words, if you wanted to figure out what this is, you take this probability and multiply it by this probability. Alright, because you are trying to start from the start and find your way to that particular branch. If you want to find multiple branches, let's say here and here, not only will you multiply along here and here to get this one, but you'll also multiply these two to now get that one. So you've done this once, you've done this as a second option. All you're going to do is now add those together. It's not all multiplication, it's not multiply, 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 multiply. It's each little branch sequence multiplies, but each additional branch you add on to that adds together. One of the things you'll come across is some experiments are quite large, or they have a large number of possible outcomes. One of the things you're going to have to really consider when drawing tree diagrams is whether or not it's worth drawing all of those branches. What we'll soon see is that some can be simplified quite nicely to either draw less branches or draw them in a way where we are showing the same sort of information but without drawing every single branch in there. Any questions so far as to like the fundamentals of using this tree diagram? Cool. Alright, well here's an example. Again, we got the coin toss example. We are tossing a coin twice. So for instance, this first little stage here is going to be the first coin toss, and then this second stage of branches here is going to be the second coin toss. Probability we're trying to find is the probability of tossing two heads in a row. So in other words, going from head to head. What is the probability of finally arriving at this head? What we're going to do first is set up our tree diagram and label all the probabilities accordingly. So in our first stage, it's 50-50, right? Heads or tails. Second stage, it's also going to be 50-50s across the board because the probability of tossing a head or a tail on the next toss has nothing to do with what happened previously. These are all independent events, which is why they maintain their probability, even though they are dependent on, even though like this would otherwise imply dependence on that. So to get head-head, just like I mentioned, that's going to be this set of branches, which is what we're going to multiply along those branches. 0.5 times 0.5, you're now looking at 0.25. Here's one of the examples where I say the branches they explode quite quickly. So we've got the numbers 1 to 3 being written on slips of paper, and they are pulled out of the hat twice. Each time it's pulled out, it is replaced before the next is drawn. So in other words, if I draw a number out of the hat and it comes out to be 1, I put that the slip of paper that says 1 back into the hat, shuffle it up, and then draw the next one afterwards. So already you can imagine just doing that twice has already got you quite a few different outcomes. As soon as you get to like the third, you're now tripling this. So one of the things I'll typically do is, if I can, not necessarily label each of the branches. Right? If you already know it's a third probability for each of these, there's no real need to go a third, a third, a third, a third, a third, a third, and so on and so forth. You can just say a third all, or you can even draw like a little arrow connecting them all together, just for your own visual understanding of what's going on. Furthermore, what you could also do is look at the actual probability that's being asked and only draw the branches that are relevant to that. For instance, find the probability that both numbers drawn are greater than 1. Well, greater than 1 simply means that's just never going to happen, right? Like that whole part. Drawing a 1 and then the whole stage up there, or drawing a 2 and then drawing a 1, not going to happen either. So we can selectively cut out those pieces of the tree diagram when we're drawing it ourselves, so long as we still maintain the original probabilities of the thing. Don't change these to 50-50s just because there's now 2 outcomes. We're selectively pruning those ahead of time simply because we don't want to draw them. They are still technically there, so don't forget them. So maybe one thing you'd want to do would be draw the initial one out, or at least have a good idea of what that would look like in your head, the first little stage, and then knowing that's going to repeat, okay, now I only draw the next little bits that I actually need. The good thing about doing this is that you've also done the processing of the question ahead of time, right? When it comes to now calculating your probability, well, because you only drew what was relevant, so all you're going to do is multiply along what you see directly. There's no further thoughts to be had. So you need to kind of do this anyway. You already need to prune these branches as is, so you might as well make the most of it and not draw the ones, or not waste time drawing the ones that you know you're not going to need anyway. Yeah, so all I've done is multiply along all these branches because we're looking for the probability of drawing a number greater than 1, of which all these outcomes have. Any questions about any of that so far? Sweet. If you have even larger number of branches, then it's the same sort of idea where you're looking at the probability that's being asked itself and then pruning from there. So you'll never really get to a stage where you have to do this sort of thing. And if if for whatever reason you do, there are typically other ways of representing the same data. Like for instance, you can do like a two-way table, but we'll look at that in a bit later. For now, if you do need to use a tree diagram for whatever reason, here's one of the things you can do. So probability of rolling 3 6s in a row or 3 1s in a row. Already off rip, we're not going to need that, right? Because we're only caring about rolling 1 1 1 or 6 6 6. So even me just showing you this here isn't the full sample space, right? We're trying to do this 3 times, so there should be an additional stage out here, and each of these should have a number of 6 outcomes on them each. So we're going ahead and simply just pruning again all those branches that don't matter, so long as, of course, we're maintaining the probabilities of those branches. At this point, we'll start making note, or we'll take note of the specific notation that I'm using here. So when you write your actual probability statements as your final answer, you do have a little bit of freedom as to how you actually define this. Like, for instance, the question asked, what is the probability of rolling 3 6s or 3 1s in a row? The keyword or there implies you can have one or the other, or both. But in this case, there's no way to do both because, well, if you rolled a 1, you can't then go ahead and roll 3 6s in a row because one of those outcomes is already a 1. That's where the union will come into play. So that's this symbol here, which is the joining. You pretty much will use this always when the keyword or is used, when you can have one outcome or another. As for what you write either side of it, just be succinct and descriptive. Just whatever's the neatest, succinct way of saying what you're trying to calculate, as long as it'll make enough sense to your teacher or the assessor, that's all that really matters. There's no like very specific terminologies to use here. But yeah, we wanted all 6s or all 1s, so again, multiplying along those branches and adding the results. Those are the basic examples of tree diagrams and how you can break down the number of possible outcomes that you have to actually draw. What's more likely to get in like a SAC or exam scenario is going to be when you have different probabilities along the branches. You'll be able to spot these quite quickly because they are a massive block of text, firstly, and what you'll notice is the wording of the question is going to be basically someone choosing between 2 different options, but depending on what they chose the previous day influences the chance of choosing the next option on the next day. Like for instance, this statement here. If she orders a coffee on one day, the probability she orders a coffee on the next day is 0.5. So if this, then that, and you'll have another statement following right after. If this, then that. When you have those 2 statements pretty much back to back together, it's already telling you that there is a sequence of events happening. If this happens, then another thing happens. And because there's 2 of them back to back, we have enough information to effectively complete our full tree diagram with that information. As for how you start, simply start by figuring out what are the 2 outcomes. So in this case, it's going to be a pie or a coffee that is being ordered for a lunch. Because apparently you can or should order a drink for a lunch. So I've got M for the meat pie, C for the coffee, and that's where you would start initially. Like none of these would be labeled just yet. From there, there's always going to be a statement that tells you what has happened previously. Because if your 2 probability statements are based on something that happened previously, you need to know what happened previously. So in this case, we're told on the first day of the week, there was a coffee that was ordered, which is why we're going to start that one out as C. So we have our initial starting a coffee, and then the 2 possible outcomes of the meat pie and the coffee. Now, because we know we started with a coffee, that's where this conditional is going to apply. If a coffee was ordered, the probability of a coffee on the next day is 0.5. So, with that in mind, we label 0.5 for that coffee branch following a coffee. We weren't told anything about this one, but we're going to make use of our complement probabilities. We know there's only two outcomes. You either get the meat pie or you get the coffee. So if this one's 0.5, this one must therefore also be 0.5, because they both have to add up to 1. Then from there, typically what will be the case is, when you have these duplicate outcomes, right, when you have like C following C, you pretty much just copy what you just did and put it back down. Why? Because this whole set of branches only exists because C was previous. So that means that this whole set of branches should also only exist because C happened, right? You just look at whatever was previous to fill those out. So a lot of the time you're able to do this and then copy that right down there. If you don't remember that on the day, that's totally fine as well. Just make sure you, again, go back to fundamentals. Okay, a C just happened, cool, that means 0.5 for the next one. What will be different is going to be the branch that follows M, obviously, right? We're not starting with a C anymore, we're starting with an M. What happens when we start with an M? Well, that's the same thing as not ordering a coffee on that day. Probability of coffee on the next day is therefore now 0.8. So once again, label that branch 0.8. And once again, 0.2 is now going to be for our complement probability. That's going to get us a full tree diagram. Then, whatever the question asks, again, you're just following the whole principle of multiplying all of the branches and adding whatever you need to. So, in this case, what is the probability of a coffee on the third day? Well, that's going to be either here or here, because that's day 3, that's stage 3 of our scenario. So, to get to here, we would have to do 0.5 times 0.8, that's that one. Or, to get to here, that's going to be 0.5 times 0.5, which is that one there. Once again, adding up the results. These are the hardest ones, oddly enough. They're a big block of text, but hopefully now that I've shown you what all the key relevant information is, there's a lot less mysticism around it. You're going to have two conditionals, two statements that say probability of this given that this happened, probability of this given that this happened, and finally you're going to have your starting point, so you actually have something to go off of. How's that? Anything to clarify there? Okay, last up we'll have a look at our sample space tables. So, as I sort of alluded to earlier, some of the experiments that we look at aren't super great to be explored via tree diagrams. Like that example of rolling 2 6-sided die. I still didn't draw the whole thing. There's 36 outcomes. You don't want to draw 36 branches and label them each individually. Not great, not fun. So long as you have 2 stages to the experiment, you can reasonably depict it using a two-way table. Now, one of the challenges you might run into here is if order does matter in that scenario, you're going to have to start labeling either your row or your column as stage 1 or stage 2, just to make sure you don't lose track of what is what. Like for instance, this is rolling 2 dice. If you needed to care about what the first dice was and what the second dice was, make sure you label on your actual thing which one's dice 1, which one's dice 2. But yeah, so in this case we are rolling 2 6-sided dice, and we're going to find a bunch of probabilities using the sample space table. One of the things I'll be showing here is what you put in the center of your table will actually be determined more so based on what question is being asked, rather than just the raw sample space itself. Like in this example here, because it was asking the probability of rolling the same number twice, what I'm putting in the intersections of all those cells are the individual numbers that were rolled, right? So this one, for instance, is rolling a 1 on the first dice, rolling a 1 on the second dice, 1, 1. Once you have that, it becomes quite clear and easy to figure out what your probability is for same number. 1, 1, 2, 2. There's 6 total outcomes out of a total possible outcomes of 36, sorry. Whereas if you have a different kind of question, which is to find the probability that the numbers add up to a number greater than 8, now what you're putting in here is a little bit different. It's going to be the addition of all those numbers, because we actually care about what they're being added up to. So, same sample space of 1s and 6s, but because the question is asking about the addition of the numbers, now we're going to try and put that information in. Once you have that, again, like these, even though it looks like a lot to fill out, there's a lot of symmetry in there. Like 1 plus 1 is 2, 2 plus 1 is 3. Oh, look at that, it just counts up by 1. Oh, look at that, it also counts up by 1 down this way. And you can fill this out pretty quickly. And then yeah, from there, once you have the whole thing labelled out, or at the very least the minimum of what you needed, you just count the number of outcomes that you wanted, divided by the total number of possible outcomes. Numbers greater than 8, so non-inclusive, that's going to be all these 9s and above, of which there are 10 total, over 36 for the total sample space. Information dump. Is there anything to clarify about any of those? I'm hoping a lot of this is revision for most people, but happy to dive into more detail if we need to. Okay. Cool, let's crack on then. So we're going to have a look in a bit more detail as to what I was talking about with the union and intersection. So I mentioned it before, union, the U symbol there, you're kind of thinking about either having one outcome or the other outcome, or both. That's why everything in the Venn diagram here is highlighted as far as the events A and B are concerned. You're also including that intersection as well. Whereas the intersection symbol there, the N, is just the join between the two Venn diagrams there. Now, as far as the union goes, I do want to specify it is not the entire sample space. Otherwise, the union would always be 1, right? Because that would include all of this as well. We're just looking at A and B when it's talking about the union of A and B. Because there are other things that exist outside of the events. Those are going to be the well, the other outcomes that you're not tracking in the scenario that you're looking for. As at this stage we come across, I think, our second equation of today's lesson, which is, I think they call it the addition rule. I've always referred to it as the union equation. Doesn't really matter what you call it, so long as you have it written down somewhere. So we can always calculate the union between two events by knowing the probabilities of each given event and then subtracting the intersection from that. Now, this was something that was a bit weird to me in school because I wasn't super bright, I guess, and I always thought, hang on a minute, if the union includes the intersection, why are we subtracting it? Before I give that away, does anyone want to take a stab at why we're subtracting the intersection here?
Otherwise, you'll count it twice.
Otherwise, we'll count it twice. Exactly right. Probability of A, all this stuff. Probability of B, all this stuff. You'll notice that the intersection exists twice there, so we need to subtract at least one copy. Nice. That was something I did not clock in high school. I just kind of said, cool, okay. I guess we're just using this equation. Cool. As for notation here, it doesn't actually matter what order you write the terms in. So for instance, the intersection of A and B is the same thing as the intersection of B and A. Right? I've just swapped the order of the B's and A's there. Same thing with the union, right? You're still just describing the relationship between one event and another. The order is irrelevant when it comes to intersections and unions. As for where those start to come up, I kind of mentioned it a bit before. Keyword OR is typically reserved for unions. So in this case, finding the probability of drawing an ace or a heart. You want to find probability of aces, probability of hearts, probability of a heart and an ace, because again we're using this the union equation here. Once we have all these terms, add and subtract. That's what we're doing there. As for where we're getting our numbers from, there is a assumption that you guys understand the insides of a standard deck of cards. For those who aren't too familiar, you've got your 4 suits, which are the different, like you got the heart, diamond, club, spade. Each of those has the numbers 1 through 13, where the 11 is your jack, 12 is your queen, and the 13 is the king. And total of 52 cards in the deck. So, 13 by 4. Which is why all these denominators are 52. You got a total of 52 cards in the deck. Which is why I'm able to immediately say there are 13 hearts in the deck, because it's a quarter of the deck. As for what intersection means here, intersection means it is both one thing and another thing at the same time, which is why when we think about ace intersecting heart, we literally mean the ace of hearts, which of course there's only ever going to be one number paired with one suit in that deck. Once you have all those probabilities, add them all up and do the final subtraction. One final thing I'll touch on here is, notice I haven't simplified these probabilities ahead of time. The reason I've done that is because I know I'm going to be adding and subtracting these anyway, so having them all being the same denominator is going to be a lot nicer than if they don't have the same denominator. So yeah, a little bit of pro tip there: when you're doing these sorts of things, only simplify it like the very end and try to keep them as the biggest possible shared denominator between them. That way, when you're doing your actual arithmetic on the things, it becomes a lot easier to work with, and you're not wasting effort. I think this will be the last example. Yeah, cool. Finally, we have a look at intersections. So this is where you essentially get a whole bunch of data points given to you in a sequence, right? So like, we got this group of 50 people and we're surveying how they spent their weekend. 35 said they went to either the beach or the movies, or both. So again, that's sort of like your union representation there. It went to beach, movies, or both. One or the other, or both. Of the 22 who went to the beach, 12 also went to the movies. So because these are all in the same sort of sentence there, it's implying that the 12 is a subset of this 22 that went to the beach. So you need to start watching out for those sort of things, because that's how you start figuring out what's intersection and what's union, right? Because this is part of the group that also went to the beach, it means they went to the movies and the beach, which is why that 12 is going to be considered the intersection of this scenario here. The actual question that's being answered here, or asked here, doesn't necessarily matter too much for actually creating your Venn diagram. There's no real shortcuts to not fill out the whole thing, or at least you can, but like, it gets a bit iffy, and you kind of want to have the whole thing anyway, just for the sake of seeing that it all adds up and makes sense with what you've created. As for how you start filling it out, typically it's easiest to start with the most specific information and then work your way out. And what I mean by that is, a group of 50 people is kind of just a group of 50 people. Whereas this 12 here is people who went to the beach and also the movies. It's got the most attached to it. It's the intersection. You start with the thing that is most honed in and specific. Then from there you sort of unwrap from out there. So for instance, we started with this 12 here. Well, there's a further 22, or it's part of a subset of, or I guess a macro set, whatever you would call that. This is the subset of that. Point being, there's a further 10 people who just went to the beach, but not the movies, right? Because this 12 belongs to this 22. Which is why when we go to our beach section here, beach excluding movies is going to be 10. From there, the next bit that we had was 35 went to either beach or movies or both, which means the sum of all of this, of beach, movies or both, has to add up to 35. So if you know this is 12 and this is 10, we're going to have 13 as well for that last little bit there. So, the information didn't say of X number of people, these guys went to the movies, kind of like how this one was. What you'll notice is there'll be different ways of saying more or less the same thing, and it's going to depend on what information you had previously. which is why it tends to be better to start with the most specific stuff and then work your way out. Because if you just try and find this without knowing these, you're going to get stuck. Anyway, not forgetting the last little bit, just because you filled this out doesn't necessarily mean you've finished the full Venn diagram. We do have this final thing here, which was 50 people total, but we're going to notice that only 35 are actually in the Venn diagram. So there's going to be a total of 15 that are not actually in or didn't go to the movies or the beach. Once we have that, you can answer any question that's being asked. In this case, it was people that went to the movies but not the beach, so that's movies excluding beach, 13. That ends up being an intersection, so it's the intersection of movies and not beach. So not beach is going to be all of this sort of stuff, and movies is going to be this. So whatever intersects those two things, which of course is just going to end up being that bit there. Cool. Okay. Have I talked enough? Have we got an idea of what's going on here? Is there anything that I should clarify about that? Cool. Okay. I'm a bit mindful of time, so I think what we'll do is we'll take a break from that little data download there, and we'll address some student questions here. So I was asked to have a look at 5E Unit 1 and 2 question 8. Am I there? 5E Unit 1 and 2 question 8. Yeah, okay. Cool. Specify the function represented by this graph. Okay, so back into the piecewise section here. Let's have a think. So all the previous questions that we had in this chapter was, you've got the piecewise function already written out, now draw the graph. This one is, here's the graph, now figure out the piecewise. Does anyone want to take a stab at how we might be able to create our piecewise function from this graph?
All the equations, I don't know if the lines look like linear, so pre-linear equations.
Yeah, exactly right. So we can see how they're all a bunch of straight lines connected to each other. So we can assume that because we can clearly see like 3 distinct joinings there, that we're going to have basically 3 linear equations. Yeah, absolutely. So 3 sort of sets of y equals mx plus c, which is good. As for how we're going to find those rules, what might we be doing?
Y minus y1 equals the m of x minus x1. You can use that formula.
Yeah, that'd be the gradient point formula. Yeah. So you have basically this generic y take y1 equals m, which is y2 take y1 on x2 take x1, m x take x1. So what he's suggesting here is that as long as you have or know 2 points on a linear, you can figure out the equation of that linear by identifying what's your x1 y1 and what's your x2 y2. You'll notice that everything in here is either x2 x1 or y1 y2, which we can do here. Right, if we look at that first sort of section there, we'll see that it's starting at x equals -3 and kind of ending at x equals -1. You got to kind of just sort of take it for granted that those are supposed to line up with the intervals that are given there. So it doesn't really matter what you call your x1 y1 or your x2 y2, so long as you keep it consistent. So let's say -3 0 will be our first point there, -3 0, and our second point is going to be -1 2. Looking at that first section there, I'm going to call this x1 y1, I'm going to call this x2 y2. And I would be literally writing that out on my handwriting, simply because I don't want to be in a case where I'm thinking, oh shit, hang on, which one was 0.2 and which one was 0.1. From there, we're just subbing into the equation and simplifying. But before I do, I should probably check. Does anyone need a refresher on what this actually is? You might have seen it more similarly as y take y1 equals m x take x1. We looked at this in the tangent lines. Does anyone need a refresher on what that actually is? Because all I'm doing is basically expanding out the gradient portion of that into rise of a run. y2 take y1 on x2 take x1. Okay, and then we'll just go from there. So for that first equation, we have y, whoops, keep putting that equal sign a bit too early. Y take y1, which is 0, equals y2, so that's that 2, take y1, which is 0, over x2, negative 1, take x1, so minus minus 3. X and x1 was minus 3, so again, minus minus 3. From there, y equals 2, so that's going to be negative 1 plus 3, so 2 over 2, which is 1. Y equals x plus 3 for that there. Which should make sense if we look at our graph.
I feel like that doesn't really click. The gradient, you got 1.
Yeah.
Yeah, that's a bit confusing to me, because like it's going from negative 3 to 2 over, like, it goes, the run is 3 and the rise is 2, so shouldn't it be like 2 over 3?
The run is 2. The run is 2. It doesn't stop at 0, it stops at negative 1.
Yeah, it's negative 1, 3 to negative 1, negative 3 to negative 1.
Yes, so this would be a distance of 1, and then this would be a distance of 2.
Oh, yeah.
Yeah.
Alright, okay.
Yeah, you can also think of it as the, if you start plugging in as well, which would be, you know, what would be the x-intercept of this? So what will make this x equals 0? Oh, sorry, what would this make this? X equals negative 3? Well, if you chuck in your negative 3, you get to 0 there. But yeah, good point. So it would be true if like this continued on, and it'd be a bit easier to see when it hits like the y-axis itself. You can see it's trending towards a y-intercept of 3 there. But no, it's really good to have these sort of like little red flags like, hang on a minute, something about that doesn't seem quite right. Let me double check my answers. So good instincts. But yeah, that's going to get us our first equation there. So just putting in the x plus 3, because the y is already sorted out by this f of x here. And all we're going to do is put the associated domain of that, which we can literally just look at from negative 3 to negative 1. Now, here's where there's a bit of interpretation to be had. You need to definitely put inclusive on the negative 3. As for the second bit, it's up to you whether you want to make this one the inclusive or whether you want to make the next one the inclusive. Typically what you'll see the textbooks do is they'll make all of like the left hand sides inclusive and all the right hand sides exclusive when they join. But it's perfectly valid to have it one way or the other. You can have this one a square so long as you make that one a circle bracket. Yeah, so that's the first of the 3 there. We're basically just going to repeat that process for the last 2 things. So for instance, if we look back at the graph again, we can see it starts at negative 1, 2, and it ends at 2, negative 1. Those will be the next sequence of points to sub into our linear. Then the third one, you'll get from 2 to 2, negative 1, all the way to 4, negative 2. Repeat that again. Does anyone want me to do the full set here, or are we fair enough with what's going on now? Alright, next one up. 5F, question 8 and 9. Okay. Find two quadratics f and g such that these points exist and both have the same maximum value of 18. Cool. That's a fun little one. There's a lot of similarities between them, and not a lot of room when it comes to quadratics for new terms. So I guess we'll see, because you've got the quadratic ax squared plus bx plus c. You've only really got 3 coefficients to work with there. 1, 2, 3 known pieces of information. This will be a fun one. Okay, let's have a think. So we've got our points that exist on both f and g, and they end up being the same thing, actually. So f of 1 and g of 1 are both 0, f of 0 and g of 0 are both 10. So we know, we know those are the same. Oh, they also have both have the same maximum of y equals 18 there. Lots of information. One of the first things we'd want to be trying to do is put that into equations. What kinds of equations might we be putting those into?
Maybe the turning point formula.
I like turning point formula here, yeah. Why did you specify turning point formula for it?
It includes all the points, I guess.
Yeah, that's right, because you saw there was the maximum value there, and you're thinking, well, okay, if I use the ax squared plus bx plus c, I'm not going to really have a good spot to put my maximum value in there. And so, yeah, using turning point form, we actually have now a spot to put it in. So f of x is generically that, so too is g of x. Those two are the same thing. As for our substitutions, so what are we going to start doing with these equations? We've got a lot of information that we could use, and we could actually use pretty much all of it in any order. It's not really going to matter where we start. Any suggestions?
Are you sure the g of x and f of x are equal?
The generic form of them, they're not going to be the same, you're right.
Oh.
But what I'm trying to write there is the generic form of them are the same.
Oh, okay.
Yeah, so that's, you're right, I probably shouldn't have written that. Yeah, what I'll do is I'll just copy this down actually. Or not. Oh, that's not the right button. There we go. Yeah, I'll just quickly tidy these up so they do look a bit different. A1, H1, C1, A2, H2, C2. So these could reasonably all be different coefficients, perhaps. With that in mind, what are we going to start doing?
Insert the values.
Yeah, just inserting them all. Doesn't really matter what order, let's just do them in the order they're given. F of 1 equals 0 would now look like f of 1 equals 0, which is, okay, so we're just having an x equals 0 there. A bracket minus h squared plus c1, 0.
See, both formulas will be 18.
Yeah, you're right. So you're saying the maximum value of 18 is referring to the y value specifically, which is therefore the plus the vertical translation of it. So yeah, we do actually know what C1 is as well. So h being negative, squaring it is going to put it right back to being positive, and you got the plus 18. Nice. I'll rewrite this as h1. Just so we're clear, it could be a different h. That's the first one. And we also got g1 equals 0. So g1 equals 0. And that should now be the exact same thing. So a bracket minus h2 squared plus 18. 0 equals a h2 squared plus 18. Next up, we got f0 being 10 and g0 being 10. So just putting a 10 there and a 10 there again. So yeah, because it is just, oh, actually no, it's not, because it's subbing in x equals 0 now. So that's, oh, which means I wrote the wrong thing. Okay, those are the 10s. Whoops. Kind of got my points back to back because it's f0 and g0. Okay, whoops. Let's do these ones properly then. Got f1 is 0, so a bracket 1 minus h2 all squared plus 18. That's kind of all we can do there. And then g1 is really, I thought I had do not disturb. g1 0 a bracket, oh, that should be h1 actually. 1 minus h2 all squared plus 18. Okay, there's a bit of mucking around there. We'll just do a quick sanity check. So we got our f1 0, g1 0, and I did definitely sub in the x equals 1 for both of those. Cool. f0 10, g0 10, f0 is 10. Yep, g0 is 10. Cool. Okay, we got a whole sequence of equations there, and we've already used our maximum value of 18 in both of those, or I guess all four of them actually. So we kind of got these sort of sets of equations, right? You got like these came from the same sort of thing, these came from the same sort of thing. It's probably not the greatest way of pairing them because you typically want to pair things in terms of where they share variables, right? So for instance, the h1s should probably pair with the h1s, and the h2s should pair with the h2s. With that in mind, how might we start solving for these unknowns?
Since some of them are since f of 0 equals to 10 and g of 0 equals to 10, we can set f of 0 equals to g of 0, and same with the other values.
So comparing these two equations together,
Um,
because that's f0 and g0.
yeah.
You can. Problem is when you compare those, you're going to have three variables now, a, h1 and h2. And it makes it a little bit challenging. Whereas if you can think of a way to pair, so I'll just label these so it's a bit easier. That's equation 1, that's equation 2, that's equation 3, that's equation 4. Because if you can find a way to directly pair the h2s and the h2s, now you've only got two variables. A, well I guess this should also be a1, a2 as well. The a's and the h's compared to the other pairs of a's and h's. a1, h1, a2, h2, a1, a2. Is it a bit more clear why we want to merge those ones together?
Yep.
Cool. As for how we're going to do it, this is basically just going to be substitution, right? So it's not immediately ready to substitute.
Do you take the 10 to the other side so it's both equal to 0?
Yeah. Yeah, that should be fine actually. I was going to maybe get the coefficient on their own, but that's actually probably better. So rewriting 1 as, so 10 to the other side, so you got now a1, h1 plus 8 equals 0, rewriting our 2 as the same thing, but it's now a2 h2 plus 8 equals 0. And you're right, because these now equal 0, we can compare the f1 and our equation 1 together by just sort of replacing both of those. So let's start with the first one there. So we're now going to have a1 h1 is equal to a1 bracket 1 minus h1 all squared plus 18. Lucky us, a1 is a coefficient on both of those as a multiplier. So no, that's not the true either, because if we divide, we're also going to divide this. Bugger. Maybe we did need to do a substitution. I was hoping that would just sort of cancel out. Okay, let's try that instead then. So rather than doing that, we'll take it a step further. Equation 1 is now going to be a1 on its own, minus 8 over h1. So now when I go here, I now have, so I'm basically subbing equation 1 into equation 3 there. I now have 0 from here is equal to a1, which I now know is minus 8 on h1. And then everything else is as before. 1 minus h1 all squared plus 18. Now I've only got one variable in there, the h1. So initially it did look pretty good to try and get the zeros, because it's like, oh shit, it's just a nice and easy get 0. But what's the more important part of the substitution is going to be actually removing a variable. That's the whole point of it. Whereas it kind of looked like they might cancel out, but because there was that plus 18 on the back end there, when you divide both sides by that coefficient, it didn't end up actually disappearing. It stayed on the coefficient at the back. But yeah, at this point now, all we're doing is trying to simplify this. I'm very certain this is a tech active, but I guess we'll just go as far as we can for this one by tech free. Minus 8 on h1, 1 squared 1, h1 squared for h1 squared, and then minus 2 h1. That's a very weird looking h there. Plus 18. 0 equals minus 8 on h1 minus 8h1 and plus 16 plus the final 18 there. 0 equals minus 8 on h1 minus 8h1, 16 and 18, 34. From here, if we're continuing to do this tech free, we're going to try to make this look like a quadratic, multiplying everything here by our denominator h1, so we've got no weird fractions going on. 0 equals minus 8 minus 8h1 squared plus 34h1, and then finally trying to condense down the size of the numbers themselves. So dividing everything by 2 seems like a nice starting point. Minus 4 h1 squared, 34 divided by 2, that's 17. And we could quadratic formula this, but we're pretty much out of time at this point. So yeah, continuing on with the quadratic formula there, we'll get you your 2 h1s. So all of this work is probably why I'm going to assume this was meant to be a tech active. So to recap, just because we did quite a bit here. First up, creating our equations. So it was decided that the turning point form will be a bit better because the question suggested the maximum value is part of the key information, and the only way we can reasonably see maximum is going to be based off of the fact of the turning point form, right? That plus c at the end is going to be our maximum. Then from there, subbing in the known points that we had, including that maximum value of 18 for the C coefficients there, and hopefully doing a better job than me of keeping track of what actual substitutions are going where. But we got there at the end. Labeling them as you go is quite nice because it allows you to finally like further process them to simplify things a bit further. Once we had all those equations and labeled appropriately, we're essentially trying to pair them up with where those additional, where the same coefficients exist in both, right? So not necessarily looking at the ones that started out the same, but the ones that will end up the same. Like for instance, yes, this were both f0 and g0, but because they are different functions, they use different coefficients. We would rather pair them up with the things that have the same labelings. Once you know what you're pairing with, it is just substitution. So get one coefficient on its own, whether you choose A1 or H1, A2, H2, doesn't really matter. Just get one of them on their own and plug it into the other. This bit, I mean, you see how we do it tech free, but I'm assuming the rest of this will be done tech active. You'll get some solutions here for H1. Yeah, actually, because you'll get two pairs, yeah, you're going to get two solutions for H actually, which will get you your two quadratics. So it didn't seem to matter too much that we needed the G pair as well as the F pair. Because I'm just looking at this now. This has got to have two solutions to it, surely. So the two H's that you get, all you're going to do is plug those back in to get your two possible A's that pair with it, and therefore two unique quadratics. I'll finish this one off on the CAS for those who want to stick around, but for now I'm hoping that was explained well enough for those who need to leave. I'll continue on for those who need to leave. Thanks for coming, I appreciate it. I'm just going to CAS out the remaining bit. Okay. So we have 93, 1, 0.
Thanks, Chris.
Yeah,
Good night.
no worries. Thanks, mate. -4, -4. I'm just going to use x for my h1. Plus 17. Oh, that should be squared. X equals 0, comma x. Oh, I already did an equal 0. That's going to get me my two h1 possible values there. And all I'm going to do is plug those back into my A equation here. So the A equation was A equals -8 on H, whatever the H was. Whoops, let's not use H, it's already defined. And so all I'm going to do is put my X's in those spots. So if I had my H1 being 1/4, then the corresponding A for that would be -32. Otherwise, it would be, what was it, 4 I think? Let me double check that. Yep. So, when all is said and done, we have our two possible quadratics, f of x, which had a pairing of, if we had a being -2, then the h needed to be +4. And I'm writing minus because we started out with x take h, which is why it's still minus there. Plus our 18. And then the other possible pair, we saw there was an a value of -32, and that came with the quarter. So we did a little bit more work than we needed to get there, which we probably should have realized ahead of time, that it was the same information being subbed into the same basic functions. But hey, lesson learned. Those are the two functions. Anything to clarify about that long string of stuff? If you guys want to like review exactly what I did here, I can put the recording live earlier if you need it. But yeah, that'll be about it. I do have more time to actually go through that last question there, because I think we also wanted to go through question 9. So yeah, if you've still got time, let me know. Happy to go through question 9 as well. What are we thinking? Yep, good to go. Awesome. Okay, find the set of values k for which that function is greater than 1 for all real x. Okay, this one will be a lot simpler, especially if we're going to assume it's cas. This one, you can literally cas out in one go. Now, I'll start with the cas thing, and then I'll do something a bit more tech-free-ish. So, what we're essentially doing here, if I think about this graphically, is I want this entire function to be over a specific value. Namely, I want it to be over 1. Now, I'm just going to mess around with it a little bit here. So y equals 1 is that. And basically, I want to figure out what k value gets me fully over that. So in this case, we need to start shoving up like k equals negative direction here to finally be above it. Now that's just to get an idea of what we're looking at, right? As for how we do it, nice and simple. This is an inequality. Where does function go greater than 1? Okay, we're going to do comma x. Find the set of all values k. Nah, comma k should do it. False. Okay. Oh right, because k is defined. When you set a slider, it actually defines it as a variable. So make sure you get rid of that. Still did it. It's definitely called F5. Oh well, now F5 is deleted. Okay. All right. Start again. Okay, now I'm just losing it. Because I didn't put the H back in. It is late, and I'm bad at things. Okay, so that's what you get if you put X. Wow, this is coming out to be quite an annoyance, huh? I would have thought that would just give it to us, but apparently not. I mean, it kind of has. The minimum of those. Alright, better idea. Set of all values of k greater than 1. So, completing the square. Right, basically making use of our turning point form and then identifying what does k end up looking like afterwards. Cas can complete the square for us. I should hope so. Cool, alright, so it can definitely do that. Now, what we saw was we need to be greater than 1 the whole time. So, in other words, the vertical component of our turning point needed to be greater than 1. If we look at what we had, we noticed it had the turning point there, and the k value was what we needed to drop it. There we go. The k value needed to be greater than 1. Or, sorry, the k value needed to force the turning point to be greater than 1. So, we're just going to take that component of it and make it greater than 1. Not forgetting, of course, to kill the define for k. I'll do that in a sec. Wow, it's not even going to let me put it down, huh? Wait, really? Did I not have to kill it? That's kind of cool. Huh, that's interesting. I would have thought we had to kill it. Anyway, that'll get that done. So, the goal there initially was to just do the inequality, but I guess the CAS just sort of didn't want to do that. So, next best thing, do what we know about in a tech-free way, complete the square, and that's going to allow us to figure out what k value would force our y value of the turning point to be above 1. Next up, show that for all k, the minimum value of f occurs when x equals 5/6. We've kind of already cheated that out from the turning point form yet again. Minimum value of f of x occurs at x, yeah, okay. So we knew our turning point was a minima, and the horizontal location of that, the x location of that, is given by the minus 5/6 here from our completed square. So that's going to shift it right by 5/6, which is why our minima is now going to occur at 5/6. All good? Tough questions, so I can see why you wanted help with them. If it's not super clear, let me know. I'm happy to try again the next day or something like that to go in a bit more detail. Oh, there is a second part to that. Find k if this minimum value is 0. Yeah, so that's going to be setting that part to 0, because for minimum value to be 0, remember this bit here is setting the height of it. So if you want the minimum to be 0, you set that equal to 0. So you're doing that. Fun. Alright, that's about it then. Nice little overtime there. Hope I didn't go on too much of a tangent. Thanks for coming. If there's anything further to clarify there, I'm happy to stick around for a bit longer. Thank you.
Hey, thanks. Have a good day.
You too. Thanks.